Hello guys, this is Keval Patil and today we are going to see design of knuckle joint. In last video we have seen the introduction of knuckle joint. Link of the video I have added in the description. Please go through that video before going to the design of knuckle. So with the designing procedure, today we are going to solve this problem too. This problem is asked in Mumbai University question paper problem many times. Okay, they repeat same problem. Problem reads, a knuckle joint is to be designed to connect two mild steel bars under a tensile load of 150 kN. So load is given P 150 kN. Allowable stresses are 70 megapascal in tension. So sigma T is given as 75 megapascal. 50 megapascal in shear. So tau is 50 megapascal. And 150 megapascal in crushing, so sigma C is 150 megapascal, and few empiricals are given. These empiricals you can find on PSG 7.139. If it is not given in the question paper, then you can find the same on PSG 7.139. They have asked, draw net sketch of knuckle joint, 3 marks, find the diameter of the rod D. Using empirical, find all dimension. With a neat sketch for failure cross section area, check all the components. Okay, so now we will move to the design procedure. So this is given data. So we'll start with the answer. Given data is force is given as 150 kilonewton. So 150 into 10 raised to 3 Newton. Sigma tension, sigma T is given as 75 megapascal. Megapascal is nothing but 75 Newton per mm square. Pascal is Newton per meter square. Mega is 10 raised to 6. So Newton per meter square. Meter into millimeter. So again it will become 10 raised to 6 millimeter. So 10 raised to 6, 10 raised to 6 gets cancelled. 75 Newton per mm square. Tau 50 megapascal. So it is shear stress 50 Newton per mm square given. Sigma C is 150 megapascal. So 150 Newton per mm square is given. And few empirical dimension given, which are already given in PSG page number 7.139. This is PSG page number only 7.139. Okay, so these empirical relations are given. Before going to the empiricals, we will see this diagram carefully. Okay, which is also given in the PSG. All right, so you don't have to remember this diagram. Directly go to the PSG 7.139 and draw this diagram. Now see what all is given in this diagram. This is single eye or eye end or rod end. This is fork end or double eye, and this is pin. So pin diameter D1 is given. Okay, then single eye, this is rod, this is also rod having same diameter D. Okay, these two rods. So knuckle joint is used to connect this two rod. Okay, now you can see this dimension is missing over here. This dimension missing, so just make it T. Okay, in PSG make correction, make it T. So this is T. T is nothing but thickness of single eye. This is thickness of single eye. Now what is the diameter of this single eye? The diameter of single eye is D2. This okay, then this diameter of single eye and double eye is same, that is D2. Okay, now this T1 is thickness of fork or double eye. T2 is thickness of pin head. Okay, and D3 is the diameter of pin head. D3 is the diameter of pin head. Okay, D2 is a diameter of single eye and diameter of double eye. Okay, D1 is a diameter of eye. So this dimension is given and their empirical relation, their values is given in terms of D. So D1 is equal to D, D2 is equal to 2D, and this same equations or same empirical relations are given in question. Okay, so first of all we have to find this D. If we know the D, then we can go for all this empirical relation. So our first job is to find the D. Okay, so we will move to the step 1. Okay, so let's say with step 1, design of rod. Okay, so now see this rod, we're going to force P, that is 150 kilonewton. We're going to apply force P 150 kilonewton over here and 150 kilonewton over here. Okay, now first of all I'm repeating this. I've repeated in design of quarter joint also. Wherever minimum cross section area, there your component is going to fail. Now for rod, okay, for rod we have similar cross section area throughout. Whenever you are designing any component, just take that single component out, remove all other component, and just single component. I'm taking this rod, I'm just stressing this rod from both sides. So now it is going to fail somewhere middle, like this, in somewhere middle. Okay, so what is a failure area? So what is failure area over here? It is simple circular. Okay, it is going to break like this, it is going to break like in two pieces, it is going to break like this in two pieces, right? So this will be the failure area. So it is the failure area. And what is the diameter? It is D1. Okay, so pin diameter is D1. Okay, so now here is a 3D diagram where you can see resisting area. It is very easy to view or understand in 3D diagrams. You don't have to draw the 3D diagrams in the question paper. What you have to do, just draw simple 2D diagram or simple failure cross section area. Okay, now this is failure cross section area. It is having diameter T1. Okay, now which stress is acting? That is tensile stress. So design of rod for tensile failure. Okay, so sigma T is force upon area. Now what is the area? So area we are having force upon area is pi by 4 d1 square. Now we know the value. Okay, sigma T is 75 megapascal is equal to force 150 into 10 raised to 3 megapascal divided by pi by 4 into d1 square. Do solve for x or do any method to your calculation. You will get d1 is equal to 50.46 mm. Okay, take next even diameter. Okay, so it is next even, so not 51, just round it off. Next even diameter 52 mm. Okay, it is ergonomics and aesthetic design. So for 50.46 do 52 mm. Next even diameter. So we got d1. Now we have d1, so we can go for empirical relations. Okay, so see, using these equations I found out all the empirical dimensions. d1 is equal to d given, d1 is equal to d is equal to 52 mm, d2 2d, so 104, d3 1.5 into 52 78 mm. So I found out all the given dimensions or empirical relation. Keep space over here. Okay, keep space over here. So if any change in d1 in further calculation, we have to reset all this empirical relation, or we have to modify all this empirical relation, or most of the cases we have to modify. Okay, so we can go to the, so now first of all, see, we have all the dimensions, so we are not going to design the knuckle joint. Now we having all the dimension, we going to check the knuckle joint for various stresses. Okay, we have all the dimensions. If you remember the quarter joint, then we found out all the dimensions step by step. Now stresses are given, empirical relations are given. We have to check all the dimensions. So here, so from step 3, there will be checking of every part for stresses. So checking of pin, checking of single eye, and checking of double eye. Okay, so we will go for step 3, that is checking of pin. So step 3 is checking of pin. Now we have pin, single eye and double eye. Okay, so first we will go with checking of pin. So first step is how pin is going to fail. So now you can see pin over here. Okay, So first thing is we are pulling this knuckle, single eye in this direction, okay, and this fork in this direction, right? Single eye in this direction, single eye in this direction, fork in this direction. So if you consider this is a pin, just consider this is a pin, okay, this is a pin. Now you are forcing it like this. This is fork and this is single eye, okay. So what going to happen, this whole part going to come out like this. It will break like this, it will break like this, and it will come out, okay. It will come out like this, it will come out like this, okay. So it broke or it fractured from here and it came out. So what is a failure area? So this is the failure area, okay. Similarly, there is one more failure area down. So this is also the failure area. So we have two failure area. What is this? Pi by 4. What is diameter? So d1 square. So this is the d1, and what this is again pi by 4 d1 square. So 2 into pi by 4 d1 square. And if you say this force, how the force is acting in this direction, failure area also this direction. So though both are the parallel to each other, then it is a shear. Then it is a shear. Or you can consider this is the axis, and if perpendicular to the axis, force is acting perpendicular to the axis, then it is a shear. Force is acting parallel to the axis, then it is a tension, okay. So this is a shear force, and it is a two area, so it is a double shear. So step 1 in this first is double shear of pin, okay. You have to draw the 3D diagram. You don't have to draw the 3D diagram, just draw the 2D diagram like this. This is a pin, okay. It is breaking like this, okay. Just consider this. It is breaking like this, okay. So this is the failure, this is the failure, this is the failure, and this is having cross section like this. So this is the failure diagram, okay. I will show you the 3D view of this, okay. First I will show the 3D view of this. So this is the 3D failure diagram. It is very easy to understand. So now what is which stress? Shear stress. Shear is equal to force upon area. So what is force? So it is P upon what is area? So area here is pi by 4 d1 square, but it is double shear, so 2 into pi by 4 d1 square. Now we know the value of d1, we know the value of P. We have to check that this shear stress which is developed in the shear of in the pin should be less than the allowable shear stress. So it is equal to P is 150 into 10 raised to 3 divided by 2 into pi by 4 into what is d1? It is 52 square. So it is nothing but value of tau. If you do the calculation, you will get it as 35.31 Newton per mm square. And what is the allowable shear stress which is given here over here? Shear stress is 50. Okay, so allowable shear stress is 50 and it is less than 50. So tau is less than tau allowable. Okay, so you can write like hence pin is safe in double shear or pin is safe in shear. I am just writing hence safe. Okay, you can write pin is safe in shear, hence pin is safe in shear. I am just writing hence safe. Machine design, you won't get enough time for attempting full question paper. You having only 3 hours and it is very difficult to attempt full question paper, so just save your time. Okay, so we'll move to the second the second, that is bending failure of pin. So second is bending failure of pin. Okay, so now how it is going to bend? Okay, so for this I will make one video, bending failure of pin. Okay, now I'm taking directly the bending moment and bending moment value. Okay, you can go and check bending failure of quarter in the quarter joint. So it is similar to the bending failure of pin. Okay, so now what is value of bending failure? MB is equal to P by 2 T by 4 plus T1 by 3. You can draw this diagram. Even if you don't draw diagram, it's all right. You don't have to derive the equation, derive the bending moment equation while solving the question. So I'm not deriving this equation. For that I will make separate video, or you can go through the design or bending failure of quarter. This equation is same like quarter. Okay, so now MB is P by 2 T by 4 T1 by 3. So we know the value. P is given as 150 into 10 raised to 3 by 2. What is value of T? That is 65 by 4 plus this is given as 39 by 3. Now it is something 2.19 into 10 raised to 6 Newton. Now we will find value of Z, that is section modulus. Section modulus for the diameter is pi by 32 d1 cube, or circle is pi by 31 d1 cube. So here we have in d1 as a diameter, so d1 cube. Z is nothing but I by y. Okay, so now it is pi by 32 into d1 value is I think 52 mm. Okay, so it is something 13.8 into 10 raised to 3 mm cube. Now we want to find the bending failure, that is sigma B is equal to MB by Z. So what is MB? 2.19 into 10 raised to 6 upon what is Z? 13.8 into 10 raised to 3. So you will get value equal to 158.69 Newton per mm square. Okay, but for us what is given in question paper, it is sigma T, tau and sigma C. Sigma B is not given. So how we can find value of sigma B? Okay, so let's check. So just take any component, just I'm taking one shaft. Okay, one shaft. Okay, this is the shaft. Okay, now it is not having any stress. Now I bended it like this. Okay, so now it is having tension over here and compression over here. Alright, tension over here and compression over here. So bending is nothing but tension and compression. Actually these values are same. These values are same. Okay, these values are same, but we consider bending value or sigma B is equal to tension. Okay, we consider big sigma B value is equal to tension value, because compression is not a failure criteria. See, compression tends to, if component has any crack, okay, what will tension does? Tension will open up that crack. Okay, tension will open up that crack, means it is a real cause of the failure. But what will the compression does? Compression just closes the crack, so it is not a failure criteria. So now considering sigma B is equal to sigma T. Okay, so now what is the sigma T value? It is 1, it is 75. And what is sigma B value? 158.69. So sigma B is greater than 75 Newton per mm square. So pin is not safe in bending. Now it is failing in bending. If it is failing in bending, then we have to increase its diameter. We have to increase its diameter. Now see, we can increase T or T1 or diameter D1. So it is better to increase diameter D1. We don't have to change the T and T1 dimension. We will just change the diameter. So remember, T and T1 we are keeping as it is. T and T1 we are keeping as it is. We are changing just its diameter. We will increase the diameter, then if it is failing, we will increase the diameter. Okay. So now what we will do in this equation, we will keep sigma b value as 75 to find the diameter. Okay, so sigma b is mb upon what is z, pi by 32 d1 cube. So now what is sigma b? We will keep it as 75 as a safe load. What is mb? mb we know 2.19 into 10 raised to 6. Remember, MB includes T and T1. So we are not changing T and T1. So we have to keep T and T1 as it is. Okay, you will understood what I am saying later on. Okay, so it is pi by 32 T1 cube. Now just put the values, put the required values. Okay, and put these values in solve for x equation in calculator, and you will get d1 is equal to 66.75. okay, is equal to next d1 diameter 67 we can take, so round figure is 68 mm. Now so d1 is changed now. So what we having in empirical relations, d1 is equal to 52 mm, but it is changed. How much it is changed? It is changed to 62. So now I'm just writing here modified dimensions. Modified dimensions. Alright. So now first thing is we have to change. First thing we have to change is d1. Okay. So d1 will become 68 mm. Okay. D1 will become 6 or DB will become 68 mm. Now D2 will become 68 into 2, that is 136 mm, and D3 will become 68 into 1.5, that is 102 mm. Now see, value of T1, T2 we don't have to change, because I already said we have kept T and T1 value as it is. So we won't change these values. We will change only T1, T2, T3. If we change T and T1 value, then this equation or this procedure is wrong, because MB will be less. MB will be you will get more value of MB. Okay, then T1 will be less. Okay, so you don't have to change the value of T and T1, only change value of D1, D2 and D3. Alright, so we will move to the next. So now we know the bending failure of pin. So we have seen the design of pin or checking of pin. Now we will move to the checking of single eye, that is step 4. In single eye we have tension, compression and shear. So we will find all these stresses and we will find whether single eye is safe or not. So first is tensile failure of single eye. So first is tensile failure of single eye, or you can write checking of single eye in tensile failure. Okay, checking of single eye or just tensile failure you wrote, then that is enough. Okay, now see, so we having single eye like this, and what we are doing, we are pulling this from this side. Okay, and we are keeping one pin in this slot, and we are pulling this pin using fork. We are pulling this pin, we are pulling this also, we are pulling this and we are pulling this also. Okay, so you can see over here this slot, it is having pin, and using this fork we are pulling this, and we are also pulling this. So what happening actually, we are pulling this and we are also pulling this using pin. Okay, so what will happen, this whole pin will break, this whole single eye will break from this side, will break from this side, and it will come out. It will come out like, it will come out like this. Come out like this. Okay, it will come out like this. Means what is failure area? Okay, what is failure area? And this portion will be like this. Okay, so this will be the failure area. This will be the failure area. Understood? So because of this tension force, this is going to break, this is going to break from here. Okay, this is going to break from here, and this will be the failure area. So you don't have to draw this diagram. What you will draw in question paper, okay, or answer sheet, you will draw this simple diagram. The failure is like this. Simple diagram. Okay, we know outside diameter of single eye, that is D2. Okay, we know inside diameter of pin, that is D1. We know the height of the single eye, that is T. Okay, so tell me the area, it is D2 minus D1 into T. So area is D2 minus D1 into T. Okay, so see this 3D view, you will understand, it will help you to understand. Okay, this is 3D view of failure of single eye. You can see the failure area. So hopefully you are understood the failure area. We will move to the solution. So now we know the sigma T is force upon area. Force is 150 into 10 raised to 3. What is D2? So modified dimension 136 minus 68. T original dimension 65. Okay, so you will get after calculation 33.94 Newton per mm square. Okay, now what is the value of allowable tensile stress? So it is sigma T 75 megapascal, and we having 33.94. So our sigma T value is less than sigma T allowable. Hence safe. Okay, so next is shear failure of single eye. Shear failure of single eye. Okay, now see this single eye, we are having pin over here, we are pulling this pin in this side, we are pulling single eye this side. Now we have seen the shear failure over here. There is one more possibility, that this whole section from here, this section will come out. Instead of here, it will fail over here. Now this area is parallel to the force applied, then it is shear failure. How it will come out? This whole section will come out like this. Like this. So the whole section will same failure that side. Okay, this is 3D view of failure area. Okay, so what is a failure area? So failure area is this T. Okay, and what is this now? What is this? Okay, now see this diameter, we consider it as this thickness. Just consider this as this T. We can't find this one, so we have to consider this thickness. Okay, now what is this value? This value is nothing but this we know, this whole diameter, the big diameter is outside diameter, that is D2. This is inside diameter D1. So it is nothing but D2 minus D1. So D2 minus D1. So we'll get this plus this divided by 2, because we want only this D2 minus D1. You will get this minus this is equal to this x, also x. So x plus x, 2x is equal to D2 minus D1. So x is equal to D2 minus D1 by 2. So this thickness is nothing but D2 minus D1 by 2. Okay. So what will be the area? So failure area is D2 minus D1 by 2 into this thickness T. Okay, T into this, but we having two areas, like this area and this area. This area also failure area. So into 2. So this 2 and 2 gone. So failure area is nothing but D2 minus D1 into T. Now, which diagram you are going to draw in the exam? You just draw this 2D diagram. Okay. Okay, and the failure is like this. Failure is like this. Okay. So it is D2 minus D1 by 2, and this is T. You just draw this diagram in exam. Now we know shear stress is nothing but force upon area. Force is 150 into 10 raised to 3. What is area? D2 minus D1 into T. So what is D2? 136 minus 68 into T, 65. Now if you compare this with this, then it is same. So for tensile failure and shear failure, we having same area or same value. So we can say this is nothing but 33.94 Newton per mm square. Alright, so we having same value 33.94 because we having same 150, 136 minus 68, 130 minus 68, 65. Okay, so I will show the 3D diagram of this just to imagine how it occurs. Okay, just see this failure. Hopefully you have understood the shear failure. Now we'll move to the next part, that is crushing failure of single eye. Now what is crushing? So I have explained in the quarter joint video. The crushing is nothing but two parts in contact, but they are not having any relative motion. Two parts in contact, but they are not having any relative motion. Okay, if two parts in contact and they are having no relative motion, then there is crushing or compression. If they are having relative motion, they are having relative motion between them. They are also having pressure or compression and relative motion, then we will call it as bearing failure. Right? So now just consider this single eye. Okay, now this pin which is inside will, now when you are pulling this pin, you putting this pin inside this slot and you pulling this pin, it going to touch this surface like now consider this is a this is pin and this is a pin and this is single eye. When you are just pulling this pin from this side, it going to touch at this surface. There will be some gap here, but it will touch to this surface. So now in this case the pin will touch at this surface, but there is no relative motion, so we can say there is a crushing. Okay, now what is the area of this crushing? Okay, just consider the area of the crushing or crushing area. Okay, so pin is touching to this surface. Okay, but what is the maximum load? Where is the maximum load acting? When pin is touching like this, maximum load will act at this point, and it will be less and 0 at this point. 0 at this point, it will be maximum at middle point. Okay, it will maximum at middle point and it is 0 at this point. So you can say this load is maximum at middle and 0 and less at this point. At this point also it is less. So now how to consider the area? We can't consider this whole area because the load is not uniformly acting. So in this case we use projectile area. So what is projectile area? Projectile area is simple. When you're having area is something like this, okay, area is something like this. You just see from this side and see the top view. You will get top view like this. So this is nothing but projectile area. So projectile area is nothing but this middle area. So it is nothing but projectile area. So here if you see from this side, you will get projectile area like this. Projectile area like this. So what is the projectile area? This is nothing but diameter. So that is d1 inside diameter, and this height is t. So projectile area is d1 into t. Simple. Okay, just see this 3 diagram and try to understand. So projectile area in case of single eye is d into d1. Alright. So just remember that whenever two cylindrical surfaces are in contact or in crushing stress, not in bearing or crushing stress, then just consider the projectile area. So d1 into t, so area is d1 t. So we know sigma c is equal to p by a. Okay, now what is p? 150 into 10 raised to 3. What is a? d1. What is value of d1? So new value, that is modified value of d1 is 68 into what is value of t? T is value of 65. So if you see this equation, 136 into 68, but 150 is the same. This is 136 minus 68. Again it is 68 only because it is 2d. Okay, d2 is nothing but 2d and this is d. So again it is 68 into 65. So you will get same value of 34.94 Newton per mm square. So now sigma c is less than sigma c allowable. Hence safe. Hopefully you understood this 3 steps of single eye. So first step was tensile failure, this diagram, then shear failure, this diagram, then for crushing failure, this diagram. Right, now we will move to the double eye. Okay, so why double eye is simple? Okay, if you understood the single eye, then double eye in like within a few seconds you will understand. Okay, now see what is the difference between double eye and single eye. So double eye is we having 2 eyes, in single eye we having 1 eye. Okay, so what going to happen? Whatever area we got, we are going to get 2 areas. Because here if we are having single area, we having here 2 area with same diameter. So double eye is similar to the single eye. Double eye is similar to the single eye. Only we have to consider whatever area we have got, we have to consider twice that area. But the thickness will change. We have considered T as a thickness for single eye. For double eye, we will consider T1 as a thickness. Okay, so what will be the change? Area will be d2 minus d1 into t1, and here will be 2. So 2 d2 minus d1 into t1. Here it will be again 2 into d2 minus d1 into t, and here it will be 2 d1 t1. Okay, so I have already checking of fork and double eye. So area is 2 d1 minus d1 into t1. Sigma t is p by a. Okay, similarly for shear it is area 2 into d2 minus d1 by 2 into t1. 2 get cancelled. 2 into d2 minus d1 t1. What you have to do, you just don't have to write all this, just directly using single eye equation, Okay, just multiply this with 2 and T1. Don't draw the diagram, directly solve it. It is all right, because everyone knows that single eye design and double eye design is same, only we are changing T with T1 and we are multiplying with 2. Okay, so we'll find the values. Okay, so we'll see the step 5, checking of double eye. First is tensile failure of double eye. We know the area, 2 into d2 minus d1 into t1. So sigma t is equal to p upon area. P is 150 into 10 raised to 3. We know the d2 dimension, so d2 is nothing but 136 minus 68, and t1 is nothing but 39. We haven't changed the t1, so you will get 28.28 Newton per mm square. So you know that sigma t is 75 Newton allowable, so it is less than sigma t allowable, which is 75 Newton per mm square. Allowable, spelling wrong. Allowable. Okay, so hence safe. Similarly, we will move to the shear failure of double eye. That is tau is equal to P by A. We know P, what is the area here? So same area as single eye, but multiply by 2. That is 2 T2 minus T1 into T1. So it is nothing but 150 into 10 raised to 3 divided by 2, 136 minus 68 into 39. Again it is 28.28 Newton per mm square. Okay, for crushing failure of double eye. If you want, you can draw the diagram. Even if you are not having enough time, then just leave. Okay, area is 2 d1 t1. So sigma c is P by A, 150 into 10 raised to 3 divided by 2 into d1 is 68 into t1 is 39. Again it will be 28.28 Newton per mm square. Now hence safe. So we have designed the knuckle joint using PSG. Okay, even if you get the problem like design the knuckle joint for 100 kilonewton load and the empirical relations are not given, then too you can follow the same procedure which is given in the PSG, because these all values are given in the PSG. So same procedure you have to follow. Hopefully you have understood the design procedure for knuckle joint. Okay, use the PSG, it's a simple method, don't forget. Okay, and mention the PSG page number. I haven't mentioned the PSG page number. You have to mention the PSG page number if empirical relations are not given in the question paper. Now empirical relations are given in the question paper, so that's why I haven't mentioned the PSG page number. But if it is not given in the question paper, then at this point, when we have found the empirical relations, that time you have to write the PSG page number. Okay, here we have to write the PSG page number, that is 7.139. Even when you will try the draw the diagram, after given you have to draw the diagram over here. Okay, so I'm just writing diagram over here. Okay, here you have to draw the diagram of knuckle joint. Only this diagram, no need to have this to draw this diagram, only draw this diagram, it will be enough. Okay, after that D, then empirical relation, just give the PSG page number. Then you will go for checking of pin, find the shear stress, double shear stress. After that bending of pin. We know even most of the time pin going to fail in bending, so you have to find the new diameter, then this dimension will modify. Okay, T2 also modify. Don't modify T1 and T. You can modify T2, it is again 0.5 into D, so it is 30. So you can see T2 is equal to 34 mm. Okay, Now, okay, so after that you move to the design of single eye. Design of single eye, first is tensile failure. This is the tensile failure, shear failure, then crushing failure. For double eye, we are having the same values, only 2 into area, and T will change to T1. Okay, so this is the end of the design of knuckle joint. If you're having any doubts, then comment and let me know. Okay, just like and share the video with your friends. Thank you.